teacher of Micro 2 course, and today we'll speak about constraint optimization that economists use. Economists is often defined as the study of the optimal allocation of scarce resources. The word optimal implies that we are dealing with some sort of an optimization problem. The word scarce implies that the objects in this optimization problem are not free to take on any value, but are constrained. For example, consumers' consumption is constrained by its available income. The central mathematical problem here is that of maximizing, or in case of cost, expenditure, or risk minimizing, a function of several variables, where these variables are bound by some constraining equations. The prototype problem is, so we have the objective function, and for example, we want to maximize it. This is our objective function. Where our x1 to xn belongs to Rn, and this axis must satisfy some conditions, some inequality constraints and equality constraints. For example, from G1, this I will call x, vector x, less or equal than B1, Gk out of x less or equal than B, k. These are inequality constraints, and equality constraints, for example, h1 out of x equals to c1, and so on, hm out of x equals to cm. These are equality constraints. So these g and h functions are constraint functions. For example, most common constraints are that all our variables are non-negative. This is our problem. If we have only equality constraints, only this one, we use Lagrangian as always. But what if we have inequality constraints? Let's consider this topic for today. So let's write down our topic, inequality constraints. Simplest, and we will actually use it quite a lot. If we have one inequality constraint, so and we will have two variables, so we want to maximize function out of x and y subject to this constraint. So we should solve such problem. If we will draw the area for J, something like this. This is the boundary. And the area where function J is equal than B, this area. And let us draw level sets of objective function. For example, level sets are here, and we should find the tangent point. Why I'm sure that the optimal point is here? That is true only if the gradient for our function, this is the point P, and the gradient of the function in the point P is in the same direction as the gradient for J function. So they should be in the same direction. In this case, the constraint is binding at point P. So we can write down that if the gradient of our f function in the point P equals to this vector gradient of J function, the point P, that means that the multiplier lambda must be non-negative. This multiplier, let's write down. That means that multiplier should be non-negative. It's when we multiply this vector J by lambda, and we will get vector F. So in this situation, our constraint is binding and we still can form Lagrangian. So we write down Lagrangian f of xy minus b. And solve it. Yes, and our derivatives out of x and out of y should be equal to 0. By x, and here equals to 0, and by y it is also equal to 0. So they both equal to 0. Okay. But what if maximum occurs at the point where our constraint is non-binding? I will give you an example. What if the solution is not at the boundary? Let's draw the same set. This set that we consider. And for example, our level sets of objective function are like this. This is the point for maximum. What we see? We see that in the tangent point, the gradient for function J is here. For example, it's point R, and the gradient for function F, it is the direction of the utility increase in this point. They are in the opposite direction. So these gradients are in the opposite direction, and that means that our constraint is not binding, because in point R there is no maximum, but the maximum will be here. Yes, and we maximize our function at point Q. So this point Q is local unconstrained maximum. What that means? That means that in this point, our gradient should be equal to 0. And we can use Lagrange. Use it. What we can say? We can say that the partial derivatives by x and by y should be equal to 0. But the constraint is non-binding. That means that we can set lambda equals to 0, this Lagrange multiplier. And that means that constraint function drops out from our analysis. Constraint is non-binding at maximal point. So we conclude that either our constraint is binding, let's go like this, or Lagrange multiplier equals to 0. And we can write it like lambda multiplied by minus b should be equal to 0. And this equation will be equal to 0 if Lagrange multiplier equals to 0, or if we're on the boundary. So we can write down it in conclusion that suppose we have our objective function, and in some point we have maximum on the constraint set, and suppose and let us say that we wrote down the Lagrangian, and there will be optimal Lagrange multipliers such that for our Lagrange function there is Lagrange multiplier such that partial derivative by x in this point, optimal point, will be equal to 0. Then partial derivative by y in this point will be equal to 0. Then this equation that we wrote, minus b equal to 0, and also our Lagrange multiplier should be greater or equal than 0. And this is true. This use both of them. So this is the condition. Also, we should write down here that we have this boundary condition. It is the same as to write down that the partial derivative by Lagrange multiplier less or equal than 0. And let's solve the example. We have such function x multiplied by y, and our constraint is x squared plus y squared less or equal than 1. For j function, critical point is 0, 0, and it is far away from the boundary, and that's why we can write down Lagrange function. and write down our conditions. So our first order condition, partial derivative by x plus y minus 2 lambda x should be equal to 0, then by y x minus 2 lambda y equals to 0, then lambda multiplied by our constraint x squared plus y squared minus 1 should be equal to 0. It's, you see, the third row. Then also x squared plus y squared should be less or equal than 1 is the same as to write this thing, that partial derivative by a Lagrange multiplier should be less or equal than 0. And the last one, for maximum, our Lagrange multiplier should be greater or equal than 0. For our gradient vectors to be in the same direction. If we will speak about minimization, our gradients will be in the opposite direction, and the Lagrange multiplier should be non-positive. But now we solve maximization problem. From first and the second row, we can find that lambda equals to y over 2x, and it is equal to x over 2y, or we can write that x squared should be equal to y squared. So then we use the third row, and we should consider two options: when Lagrange multiplier equals to 0, or when it is greater than 0. So first option, if Lagrange multiplier equals to 0. What that means? That means that in the solution, x will be equal to y will be equal to 0. And it's okay. It can be, it will be our critical point. But what if Lagrange multiplier is not equal to 0? Then we work on the boundary, x squared plus y squared equals to 1. And from here we will find four points. X will be equal plus minus 1 over square root out of 2, and y equals to plus minus 1 over square root out of 2. And that means that when we maximize our Lagrange function, we will have 4 points. Let's write down them. We will not be lazy. And here will be x equals to 1 over square root out of 2, y the same. And also we should write down Lagrange multiplier. Lagrange multiplier, in this case, it is y over 2x, and it is 1/2. And the next point, x minus 1 over square minus 1 over square root out of 2, and Lagrange is the same. Then we have other 2 points, minus 1 over square root out of 2, and y plus. In this case, Lagrange multiplier is with negative sign. And here also with negative sign. As we see, for maximum, our Lagrange multiplier should be greater or equal than 0. So we distract our last 2 cases out of consideration. They will be for minimum. So this we do not use because they are less than 0. So now we have three points that 3 candidates for maximum. So we plug in. So let me show them this one, and this one. So we plug in these 3 points into our objective function and choose the maximal value. And so let me write down it for you. Plug into objective function. And choose maximal value. And as you see, our objective function is x multiplied by y. If we put here zeros, the function value will be equal to 0. If we put 1 over square root out of 2 and 1 over square root out of 2, or the third point, values will be the same, and they will give 1/2, and it is bigger than 0. So these 2 points are our solutions. And what else? What conditions we also like to use and we should use when we solve our economic optimization programs? We have our non-negative conditions that our variables, for example, x should be greater to equal than 0 and y should be greater to equal than 0, so because we cannot consume -1 apple. Yes, so the amount of apples should be non-negative. How we can rewrite such conditions? We can rewrite such conditions as -x should be less or equal than 0, and -y should be less or equal than 0. And these 2 conditions also can be used as 2 more bounding conditions, 2 more these inequality conditions. And here in this Lagrange, we will write like minus, I don't know, for example, m1 multiplied by -x minus m2 multiplied by -y, and we will maximize by x, y, and all these 3 Lagrange multipliers. And conclusions will be the same. The solution will be, we will use the same technique to find the solution. But we can use not easier way, but Kuhn-Tucker formulation to solve these typical economic problems. Kuhn-Tucker rewrite this condition for Lagrange when we have these non-negative conditions. So let us write down Kuhn-Tucker formulation, and then we will solve the example. For example, we will have our usual utility maximization program. And let us write down the Lagrangian only with one constraint. It is budget constraint, but without these non-negative constraints. I'll say that it is L. Our utility as a function of x1, x2 minus Lagrange multiplier, price of the first good, x1, plus price of the second good, x2, minus our income. But also we know that x1 and x2 should be non-negative. And the solution for such problem, actually with three boundaries, but here in the Lagrange, we write down only one boundary. We can write down it in the next way. So partial derivative by x1 should be less or equal than 0. Partial derivative by x2 should be less or equal than 0. And here we will have two cases. If x1 equals to 0, it will be corner solution or not, if it is greater than 0. And we can compose them in this in the way that x1 multiplied by x1 minus lambda p1 should be equal to 0. And also the same about x2. Be equal to 0. What else? What else? We take the derivative from our Lagrangian by Lagrange multiplier, and this is okay, let's write down I minus p1 x1 minus p2 x2 greater or equal than 0. And the same we should use the same as in the second row, we should do with the Lagrange multiplier. So Lagrange multiplier multiplied by the partial derivative of this Lagrange multiplier, and it is lambda multiplied by I minus p1 x1 minus p2 x2 should be equal to 0. Do you see that we have our partial derivatives, and now they should be less or equal than 0 here also. And we will have two options: when x1 equals to 0 or when it will be positive. When x2 equals to 0 or when it will be positive. Same for our boundary. It can be binding condition or not, as we did in the previous example. So, and okay, let's solve a typical problem by using Kuhn-Tucker condition. So we will have such utility function. It is a square root out of x1 plus x2. You know such utility functions. They are quasi-linear functions. And we should maximize it by choosing x1, x2 greater or equal than 0, subject to our budget constraint p1, x1 plus p2, x2 less or equal than m. our income. So we should solve such problem. So let us write down the Lagrangian for Kuhn-Tucker. So we will not write down Lagrangian with 3 boundaries. We will write it only with budget constraint, and these 2 constraints, non-negative constraints, we will put into our solution by these multiplications here. So let's do it. So our Lagrangian is our utility function as lambda m minus 1 x1 minus p2 x2. And we should maximize it by choosing x1, x2 greater or equal than 0. Here is this boundary. And our for maximum Lagrange multiplier should be greater or equal than 0. Okay. You can rewrite these non-negative conditions as minus x1 should be less or equal than 0, minus x2 should be less or equal than 0, and you can solve it by using the previous technique. But now let's solve it by using Kuhn-Tucker technique. And here our partial derivative by x1. Easy. A over 2 square root out of x1 minus lambda p1. And this should be less or equal than 0. What we understand? We understand that if x1 greater than 0, then our partial derivative equal to 0. Where we found it? From where we found it? From this condition. You see? So if x1 greater than 0, so this bracket should be equal to 0. Yes? And if x1 equals to 0, this can be less or equal than 0. Same for x2. So here easy 1 minus lambda p2 less or equal than 0. And also understand that if x2 greater than 0, then partial derivative should be equal to 0. This is this multiplication. If x2 greater than 0, so this bracket should be equal to 0, and vice versa. If x2 equals to 0, this bracket can be less or equal than 0. Very good. Next. And what about Lagrange multiplier? Equals to m minus p1 x1 minus p2 x2. And also we can write that here in this m minus, this should be greater or equal than 0. But here we understand that it will be equal to 0. Yes? Or we can write it. So if Lagrange multiplier greater than 0, then p1 x1 plus p2 x2 should be equal to m. Same as for x1, same for x2. But if Lagrange multiplier equals to 0, that means that our boundary condition, our condition is non-binding. This budget constraint is non-binding condition, and we will choose the point in the budget set, but under the budget constraint. Okay, this is the system, and let's solve it. We have how many options we have? We have 4 options. First option. x1 equals to 0, x2 equals to 0. Second option. x1 equals to 0, x2 bigger than 0. Third option. x1 bigger than 0, x2 equals to 0. And the fourth option, x1 greater than 0, x2 greater than 0. So these are our favorite corner solutions and interior solution. This is interior solution of the problem. These are corner solutions, and this is about the origin of the axis. So what about first two? First two, easy. Because if x1 equals to 0, then marginal utility comes to plus infinity. Yes, marginal utility of the first good. Put it into derivative by x1. A over 2 square root out of x1. If x1 is near 0, this is near plus infinity. If x1 is near 0. So here will be no solution. Third option, when we consume positive amount of the first good and we do not consume the second good. Okay. In this situation, let's see. First good. So the partial derivative by x1 should be equal to 0, and the partial derivative by x2 should be less or equal than 0. Let's write down it. So a over 2 square root out of x1 minus lambda p1 should be equal to 0, and 1 minus lambda p2 should be less or equal than 0. And also, if we assume that Lagrange multiplier is positive, then m minus p1 x1 minus p2 x2, but x2 is equal to 0. I will not write it here. This should be equal to 0. From these three rows, we'll find that lambda is equal to a over 2 square root out of Okay, from here, x1 equals to m over p1, as always, because we spent all our income on buying x1. Okay, good. Then put it into the first row. Here will be m p1, and also lambda should be greater or equal than 1 over p2. And one more time, x1 equals to m over p1. We combine these two and say that a over 2 square root out of m p1 should be greater or equal than 1 over p2. And we can revert it, write it and say that we have constraint for our income, for example. So our income should be less or equal than a square, price of the second good square, over 4, price of the first good. So we will have such corner solution. It is optimal for us to buy, not to buy the second good, and to spend all our income for the first good. If our income less or equal than this a square, p2 square over 4 p1. So this is the corner solution. Well, not, as we proved, we do not have opposite corner solution. We will not consume x1 equals to 0, x2 equals to 0. But what else? We should check the interior solution, why we speak only about corner solutions. Okay, this is the fourth. When we consume both the first good and the second good. So when we have interior solutions, both partial derivatives should be equality, should be equal to 0. So let's find a over 2 square root out of x1 should be equal to lambda p1. 1 should be equal to lambda p2. And one more time, m minus p1 x1 minus p2 x2 should be equal to 0. So from here, we will find that we can divide them and a over 2 square root out of x1 will be equal to p1 over p2. As you see, it is like marginal rate of substitution equals to the price ratio, as always. And also we have budget constraint. So we put this condition into budget constraint, and we will find our amount of goods. So x1 equals to from here. x1 equals to a square p2 square over 4 p1 square, and it is always bigger than 0. Then put this x1 into budget constraint, and from here we will find that x2 equals to m minus p1 x1 star over p2. Yes, put x1. This will be m minus a square p2 square over 4 p1 over p2. And what condition we have? That we consume this good. We buy positive amount of this good when it is true, when denominator is bigger than 0, because denominator price of the second good always bigger than 0, we assume. So that's true when we have income greater than a square p2 square over 4 p1. Very good. And now we are ready. We can, for example, we can write down like demands for the first good and for the second good. That depends on the connection between income and prices of these two goods, or we can write down like this. So first option, x1 equals to m over p1, corner solution x2 equals to 0 if m less or equal than a square p2 square over 4 p1, or x1 is positive a square p2 square over 4 p1 square, and x2 is m over p2 minus a square p2 over 4 p1, and this is true if m greater than is a square p2 square over 4 p1. This or that. So this is the answer for this problem. What else we can check? What else we can check? In our Contactor solution, we also have this part. And in our solution, we assumed that our Lagrange multiplier is positive. then we should check it. We should check that our Lagrange multiplier, if we put this these parts into, for example, okay, it can be our Lagrange multiplier here. Here, for example, it is 1 over P2, it's positive. Okay, and in the first part, this Lagrange multiplier also positive. Okay, but what if Lagrange multiplier is equal to 0? That means that our budget constraint is non-binding, and we will not spend all our income. Also can check it, but we know that we will spend all our money, and you can prove it. Or you can use the previous technique to check it properly. Okay. One more time, for minimum, in the previous technique, our Lagrange multiplier should be non-positive. What else? Here in our examples, we consider only two variables, x1 and x2, and we considered only one inequality constraint and two non-negative constraints. But anyway, in our optimization programs, we can have both equality constraints and inequality constraints and non-negative constraints, and they can be mixed. And this Kuhn-Tucker formulation, or how to solve this by using Lagrange, you can use them not only for two variables and one constraint. And for more information, I have recommendation for you to read and to download and read this textbook, Mathematics for Economists, by Simon and Bloom, and all this information that I provided here, that I provided today, all theory that I provided today, not the examples, are from this book. So let's write down Mathematics for Economists. By Simon and Bloom. So if you do not know how to solve the optimization program in your homework, or when you will write, for example, scientific paper, maybe, please open this textbook, Mathematics for Economists, and there are provided a lot of techniques and I think a very complete theory for us that we use in the economics. So, okay, I think that's all. Thank you so much. Bye-bye.